In this video, we are going to learn how to evaluate triple integrals in spherical coordinates. In order to do that, we need to define the volume element dv over a spherical wedge of the region E. So the region is going to be spherical in nature. That's why we're thinking in terms of spherical coordinates. So as a simple example, it could be the sphere of radius 1. And we're going to take a small wedge from that region, try to define the volume of that wedge to create an expression for dv. So that's our first task. So we have a diagram of that small spherical wedge from a larger region, and we're going to mark this diagram up with rho, theta, and phi to define the volume. So starting with rho, we can go out here. That's going to be rho, the radius to the inner surface, which then makes this edge here delta rho, or the change in the radius from the inner to the outer surface. So if we think of the inner surface as a sphere of radius 1, the outer surface sphere of radius 2, then delta rho would be 1, 2 minus 1. So we have our first side of this region defined. Next, we'll focus on this edge, and it is slightly curved, so we are going to need an arc length computation. We have the radius as rho. We need the angle. So off the positive z-axis, that's phi. And if we continue to sweep out that arc, this is going to be delta phi, or the change in phi as we sweep out that arc, which makes this side length rho times delta phi. And then we'll focus on this edge across the back. It is also slightly curved, hard to tell from this perspective, but we're going to project this onto the xy plane, since we're going to need theta to help us here. So that is a right angle. That is a right angle. And exaggerating, there we have that curved edge that we're finding the arc length of. So we need theta. So we have theta coming off the positive x. So this is delta theta. As we continue to sweep that arc, that's the change in theta. And then we need the radius of this arc, which really is the projection of rho onto the xy plane. So if we highlight this right triangle here, the same way we did for our spherical coordinates, if this is phi, so is this, with a little geometry and alternate interior angles. Rho is the hypotenuse, which makes this side rho sine phi. And then we have this arc length to be rho sine phi times delta theta. Now, defining the volume of this region, even though some of the sides are slightly curved, remember we're picturing this to be an infinitesimally small part of the larger spherical region. And in the infinitesimally small version of this, the curvature of each side is negligible. So we can just use length times width times height to define this volume. So that means the volume is approximately delta rho times rho delta phi times rho sine phi delta theta. Rearranging this, we get rho squared sine phi delta rho delta theta delta phi. And that's for one of these small wedges. And then integrating, right, we accumulate the sum of an infinite number of these small wedges. So we're taking a limit, which turns this expression into our dv volume element. And that's rho squared sine phi d rho d theta d phi. So highlighting that rho squared sine phi, that's the important piece when setting up a triple integral in spherical coordinates. So for cylindrical, we had r dz dr d theta, so that factor of r was important. For spherical, the factor of rho squared sine phi is going to be important to include in every spherical triple integral that we set up. So now that we've established this idea, which is one of the more important ideas in this video, let's put it into applications. So if E is the general spherical region defined as the set of all points, rho, theta, and phi, such that rho is bound from A to B, theta is bound from alpha to beta, and phi is bound from C to D, so all constant bounds, and we have a continuous function on the region E, Then we can define the triple integral as the iterated integral of this function converted to spherical. So it's going to be a bit of writing here. So x is rho sine phi cos theta. Y is rho sine phi sine theta. Z is rho cosine phi. dv, as we just established, is rho squared sine phi d rho d theta d phi. So this is also a good review of our conversion formulas, since we'll need those as well. And then putting the bounds in, rho goes from a to b, theta goes from alpha to beta, and phi goes from c to d. So convert everything into spherical coordinates. Our bounds should be in terms of spherical as well. We don't forget that factor of rho squared sine phi, and then we're good to go and integrate. So our first example, evaluate the triple integral over the region E of x squared plus y squared dv, where E is the portion of the ball x squared plus y squared plus z squared is less than or equal to 2 in the first octant. Okay, so we have a sphere. We're taking a portion of that sphere that's in the first octant. That's going to define the bounds of integration. We need to convert our x squared plus y squared and our dv. So let's start with the region. So we can draw a sphere here. We'll draw the best version of a sphere that we can. Not bad. And then we're going to take just the portion of that sphere that's in the first octant. So right there. Now just marking up where we're thinking. So rho is the radius, so from 0 out to the surface of the sphere. Theta, use a different color, so theta is going to be how we sweep in the xy plane, and phi is going to be how we sweep off of the z-axis. So probably helpful to label our axes as well, and then that radius is square root of 2. Okay, so we have the triple integral. X squared plus y squared is rho squared sine squared phi. That's one of those conversions we established in our video on spherical coordinates. dv is rho squared sine phi d rho d theta d phi. And we go bounds. So rho goes from 0 to the square root of 2. Theta, in the xy plane, if we're in the first octant, that's going to go 0 to pi over 2. And phi, off that z-axis, is going to be 0 to pi over 2 as well. And what you're going to notice is a lot of trig integration is going to show up in spherical coordinates just by the nature of our conversions. And no difference here. Also the order. This is the order that our textbook uses, and we'll kind of follow, d rho, d theta, d phi. But when these are constants, these can be switched around, and you may see that as well. So evaluating this triple integral, we do have a separable triple integral, since the function can be written as a product of rho, phi, and theta, and all of our bounds are constant. So that's just going to help us evaluate this a little bit more quickly. So we'll go phi first, so that's going to be sine cubed phi d phi from 0 to pi over 2. And then theta, so integral from 0 to pi over 2 of 1 d theta. And then the integral from 0 to the square root of 2 of rho to the 4th d rho. All right, so a sine cubed integral shows up here. So if we remember the process, factor out a sine phi times sine squared phi. Replace the sine squared with Pythagorean identity 1 minus cos squared phi. And then we distribute everything back out. So we have the integral from 0 to pi over 2 of sine phi minus sine phi cos squared phi d phi times the integral from 0 to pi over 2 d theta times the integral from 0 to the square root of 2 rho to the 4th d rho. Just rewriting all of our integration. Now we can do all three integrals at the same time. So integral of sine phi is negative cosine phi. Integrating our next term, cos phi would be RU, du would be negative sine phi. So that's going to be plus 1/3 cosine cubed phi, evaluated from 0 to pi over 2, times theta, evaluated from 0 to pi over 2, times 1/5 rho to the 5th, evaluated from 0 to the square root of 2. All right, plugging pi over 2 into cosine would give us 0, and then plugging in 0, so we have minus negative 1, so plus 1, and then minus 1/3, times pi over 2, times square root of 2 to the 5th would be 4 square root of 2 over 5. So this is 2/3 times pi over 2 times 4 square root of 2 over 5, which is going to be 4 pi square root of 2 over 15. Not the cleanest answer, but that is the value of this particular triple integral in spherical coordinates. Okay, so moving back down, let's go on to our next example. So evaluate the triple integral over the region E of the square root of x squared plus y squared plus z squared dv, where E is the region between the spheres x squared plus y squared plus z squared equals 4 and x squared plus y squared plus z squared equals 16, such that y is greater than or equal to 0. So this is a good opportunity for you to try to set up this integral on your own. You don't need to integrate, you can, but really focus on the setting up part. I'll highlight the fact that y greater than or equal to 0 means you're only going to have half of each of these spheres. It's just a matter of what half you're looking at. So try this setup, play the video, see how you did, and then we'll keep moving. Okay, so I drew the two spheres. Then in blue, I highlighted the part of each sphere that was y greater than or equal to 0. So you can see we're on the right side of the xz plane for both of those spheres. So that means theta goes from the positive x-axis to the negative x-axis, so 0 to pi. Phi goes from the positive z to the negative z-axis, so 0 to pi. Then our region is in between the two spherical surfaces, whose radiuses are 2 and 4. And then the function that we're integrating, which is the square root of x squared plus y squared plus z squared, would just be rho. And then dv becomes rho squared sine phi d rho d theta d phi. If you want to practice integrating out, this value is going to be 120 pi. But really the setup here for me is more important, and highlighting that dv with the factor of rho squared sine phi. Now find the mass of the solid below the sphere, rho equals 1, and above the cone, phi equals pi over 3, with mass density x squared z squared. So here is an application with mass. So we have our mass density function that's going to need to be converted to spherical, and then we have our region. So let's start with our region. So we have a sphere and a cone that are defining this solid. So we have a sphere of radius 1, and then we have the cone based off the phi value. So if we go pi over 3 off the z-axis, so somewhere around there, so there would be our cone. So highlighting the solid in blue, we have what is often referred to as an ice cream cone. Right? So the solid looks like an ice cream cone. And that's the region that we're integrating over. Our density function, that's going to be rho sine phi cos theta squared times rho cos phi squared. So now we can set up our triple integral to find the mass. So cleaning that up, that's going to be rho to the 4th, and then cos squared theta, changing the order slightly, sine squared phi cos squared phi, times rho squared sine phi d rho d theta d phi. Right, that's our dv right here. And then our bounds, so we're going rho from 0 to 1. We would go out till we get to the surface of the sphere. Then we're going all the way around in a circular motion in the xy plane, so 0 to 2 pi. And then phi, as we go off the positive z axes, we're going until we hit the cone, so that's 0 to pi over 3. Now we'll evaluate on the next slide. So you can see all our bounds. If we clean that up, we have rho to the 6th cos squared theta sine cube phi times cos squared phi d rho d theta d phi. Another separable triple integral. So integral from 0 to pi over 3 of sine cubed phi cos squared phi d phi times the integral from 0 to 2 pi of cos squared theta d theta times the integral from 0 to 1 of rho to the 6th d rho. Again, a lot of trig integration showing up here. In order to integrate with respect to phi, we're going to take the same approach for just the sine cubed integral, and then we'll just have this extra factor of cos squared to consider. So this is going to be sine phi, and I'll skip ahead a little bit to 1 minus cos squared phi times cos squared phi. And then we're going to distribute everything back out. And while I have the blue marker, cos squared theta replaced with the double angle identity is going to be 1/2 plus cosine 2 theta over 2. So rewriting all our integrals, so 0 to pi over 3 of sine phi cos squared phi minus sine phi cos to the 4th phi d phi times the integral from 0 to 2 pi of 1/2 plus cosine 2 theta over 2 d theta, and then the integral from 0 to 1 of rho to the 6th d rho. Okay, so integrating with respect to phi, cos phi would be our u, so negative sine phi would be du, so I also need negative 1 there. Cos phi, negative sine u, so we're going to get negative 1/3 cosine cubed phi plus 1/5 cosine to the 5th phi. Evaluate that from 0 to pi over 3. Then we have theta over 2 plus 2 theta would be u, du would be 2, so we circle that factor of 2. So plus sine 2 theta over 4 from 0 to 2 pi. And then 1/7 rho to the 7th from 0 to 1. Okay, so cosine of pi over 3 is 1/2. So to the 3rd would be 1/8. So negative 1 over 24. And then plus 1/2 to the 5th would be 1 over 32 times 5 would be 1 over 160. And then plugging in 0 would get us plus 1/3 minus 1/5. And then if we plug 2 pi in, we're going to get pi. Sine of 4 pi would be 0. Plug in 0, both terms would be 0, so times pi. And then times 1/7. To save us the effort and aggravation, we would get 47 pi over 3,360. So that is the value of the mass of that ice cream cone region with the given density function. So last thing we have to cover is what happens when our bounds are not all constant. So if E is the general spherical region defined as the set of all points, theta is bound from alpha to beta, phi is bound from C to D, so that stays the same. But now rho is between two functions in terms of theta and phi. Could be both, could be one. And our function is continuous on the region. Then we're going to rewrite this. Instead of doing the whole conversion, we're just going to say f of rho theta phi, basically go to spherical, rho squared sine phi, d rho d theta d phi. And now our inner bound of integration, g1 of theta phi, to G2 of theta phi, and then theta goes alpha to beta, phi goes C to D. Really, all that changes is we're no longer going to be able to separate the triple integral because we have a function of theta and phi as our inner bounds. So let's look at an example that would incorporate this idea. So set up an iterated integral to calculate the volume of the sphere x squared plus y squared plus z squared equals 4z. So first let's get a sense of where this sphere is with completing the square. So x squared plus y squared plus z squared minus 4z plus 4 equals 4. So x squared plus y squared plus z minus 2 squared equals 4. So we have a sphere that's just not centered at the origin, radius 2. So if we drew this out, so 1, 2, 3, 4. So our center would be there, and our sphere is going to sit above the xy plane. Now we need this in spherical, so that's going to be rho squared equals 4 rho cosine phi. So that's rho equals 4 cosine phi. Now, just like in polar, this graph doesn't take 2 pi, and phi has to go from 0 to pi anyway. So if we think about phi bounds here, to get back to the origin, that's going to be phi equals pi over 2. So if we plugged in 0, we'd get 4, which would put us here, and then to get to the other side of the diameter, we would only need the angle of pi over 2. And then theta will spin us around the z-axis to complete the whole sphere. Right, so that's another important part of this example. So we have the triple integral. Volume is 1, and then dv is rho squared sine phi, d rho, d theta, d phi. So now we're going 0 to 4 cosine phi, and then theta goes 0 to 2 pi, phi goes 0 to pi over 2. Now that's our setup. If you want to practice your integration, this is going to be 32 pi over 3, which we can actually get because the volume of a sphere is 4/3 pi r cubed, and the radius here is 2. So we can actually know this value before we do any integration. So, important takeaway for me is this dv, volume element. We practice setting up a bunch of integrals, and now practice on your own, and I'll see you on the next video.